Human societies depend on water. As such, if we want to build truly resilient societies, we must rely on resilient water systems. Climate change, increasing demographics, and geopolitical tensions pose a big risk to the provision of sustainable water services, including drinking water supply, sanitation, and drainage. This is particularly true for our cities. This critical situation has prompted the United Nations to include safe access to water, wastewater, and drainage services for all into their Sustainable Development Goals, and in particular into SDG number 6. Water managers, practitioners, and researchers agree that digitalization is key to secure a resilient water future. Thanks to technology, we are now able to sense the built and natural environments like never before, either via sensors deployed on the field, such as, for instance, smart water meters, or via remote sensing. At AidroLab, we want to develop novel artificial intelligence techniques that can exploit this wealth of data to improve the resilience of urban water systems. In particular, at AidroLab, we will focus on urban water networks, which comprise drinking water distribution systems and urban drainage systems. The former are responsible for supplying drinking water to households, while the latter essentially collect stormwater and sanitary sewage. AidroLab is an AI lab which has been founded within the TU Delft AI initiative and is built across the Faculty of Civil Engineering and Geosciences and the Faculty of Electrical Engineering, Mathematics, and Computer Science. I have the pleasure to lead this lab along with my colleague Dr. Elvin Isufi, who will now continue the presentation.
Digitalization of our daily activities is a powerful tool in our hands because it provides a flow of data that we can use to understand the underlying system, identify anomalies in it, or improve such system further. However, data themselves are just numbers. For the artificial intelligence to learn patterns in this data, we need to provide it with the context in which we collected them. Such context is often present in the hidden structure of the data. In fact, the structure is so present that it gets easily unnoticed. Think of a water system. It has pipes, pumps, and households, which all obey to a particular connectivity in Delft and to another in Rotterdam. Thus, the data collected in the context Delft will be different from the data collected in the context Rotterdam. If we provide such structural context to the AI, it will be able to identify better a flooded area, a leakage, or the water demand. Other structural data we interact with are those in social networks. When we log in our social platform, we are connected to a group of friends, which are in turn connected to their friends. Consequently, the data we interact with are tied with this structure. LinkedIn, for instance, uses this structure and the respective data to recommend us a new job position or a person to connect with. But not only engineering data are structured. Also, data coming from natural systems have a structure. One example is the brain. Neuroscientists for decades have analyzed the structure of the brain to understand its normal working conditions or its connectivity under a specific disease. The better the structure is exploited, the better the disease is understood. Nowadays, the structure is coupled with non-invasive data collection techniques such as EEGs. Altogether, these applications have entities interacting with each other through network. Thus, we want the AI to exploit such a network to perform a specific task. In network AI, I'm focusing on two fundamental questions. The first one is how to learn the best structure from the data. Answering this question will unveil hidden connections in the data in a reliable manner. Using AI for such a task will reduce the research effort and will not require an extensive expertise from researchers in different domains. The second question is how to best exploit the structure. At EMCS faculty, we are developing algorithms that best capture such structure for a task at hand. However, since the structure may be incorrect and dynamic, we would like our algorithms to be robust to such uncertainties. While this fundamental research will help us understand the basic mechanisms of network AI, Applying network AI to real-world application will make it more tangible to the end user. At AidroLab, we are applying these techniques in water networks. I'm passing now the stage back to Ricardo to tell us more about this exciting direction.
Thanks, Elvin. Indeed, at AidroLab, we want to develop new network AI models for urban drainage systems and water distribution systems. We will do so by feeding not only the sensor data to our AI, but also information related to the structure. For instance, we will provide a graph that describes how the network of pipes, conduits, and canals link together all the nodes of our urban water systems, whether these are manholes or households, storage tanks, and so on and so forth. By employing all this information and additional external data, such as meteorological data, our network AI models will be able, for instance, to assess the resilience of our urban water systems. At the same time, we can use these models to actually devise new adaptation strategies to actually increase the resilience of our urban water system. At the same time, we can use this model for mapping flood risk in urban environment or optimize network operations. They can also be used for other interesting applications. In this way, we really hope that our lab can contribute to improve the resilience of urban water system and in this way help towards building a more resilient future. Thanks.